So in this video, I want to introduce you to finding the nth term for a quadratic sequence. Okay. Now I'm going to first of all start this by thinking up a quadratic nth term, and then we're going to see what the sequence looks like and how we're going to piece together what are the clues that we need to look out for, what's the process that we need to look out for to find it. So let's say that the nth term was n squared plus 2n plus 1. Okay, so what would the sequence look like? Well, let's write out the first four terms, shall we? So we've got n, un, so we're going to have 1, 2, 3, 4. Okay, so when n is 1, we're going to have 1 plus 2 plus 1. So that's going to be 4. When n is 2, we're going to have 4 plus 4 plus 1, which is 9. When n is 3, we're going to have 9 plus 6, which is 15, plus 1 is 16. When n is 4, we're going to have 16 plus 8, which is 24, plus 1 is 25. Okay, so we get 4, 9, 16, and 25. Now you might also spot that these are square numbers themselves. And the reason for that is but they're kind of shifted along by 1, aren't they? The reason for that is that this factorizes neatly. There's a perfect square, and it factorizes to n plus 1 all squared. And that is the nth term for this. That's why it's one position along. Okay, that's why you're seeing what you're seeing. But let's just imagine that we don't know this. Okay, this is kind of like hidden to us, but I'm leaving it there. So what we'd probably be thinking about is, okay, well, let's work out what the difference is each time. Can we see any pattern? So from 4 to 9, we are adding 5. Okay, so let's draw that like this. So can't leave a smudge on the board, can we? There we go. Right, so from 4 to 9, that's adding on 5. And from 9 to 16, we are adding on 7. And then from 16 to 25, we're adding on 9. So you can see that the differences aren't constant. But there is a pattern in the differences. We are adding on 2 here from 5 to 7, and we're adding on 2 to get from 7 to 9. Okay, so what this does is it tells you, because you've got this extra row, and because these are constant now, that's telling you that it is a quadratic sequence. If we had gone to a third tier, and you had had all plus 2s, then you know it would have been a cubic sequence, and so on and so forth. Okay? So, the next thing that you need to be aware of is that this number here, right, you always half it to tell what number's going in front of the n squared. So, because that's 2, half of 2 is 1, and so it's going to be a 1n squared. If this had been 4, we would have had a 2n squared. If it had been 6, we would have had a 3n squared. Okay? If it had been 3, we would have had 3 halves in front of the n squared, or 1.5. So because we now know that it is a positive n squared, what I'm going to do is I'm going to erase that, and I'm going to put n squared into my table. Now n squared would give me 1 squared, 2 squared, 3 squared, and 4 squared. And what we're going to do is we're essentially going to subtract this row from this row. Now the reason why we're doing that is essentially I'm going to subtract the n squared away. And what it should leave me is a linear sequence I can work out. Okay, so I already know the n squared is there. Subtracting it away allows me to ignore everything but now the linear term. So subtracting that away, so I'm going to un take away the n squared. 4 take away 1 is 3. 9 take away 4 is 5. 16 take away 9 is 7. 25 take away 16 is 9. So we have 3, 5, 7, 9. We need to add 2 to get from 3 to 5. Add 2 to get from 5 to 7. Add 2 to get from 7 to 9. So what we now have is a linear sequence. The common difference is 2, so that means that 2 needs to go in front of the n. And how do you get from 2 back to 3? You need to add 1. So this sequence is precisely that, as expected. So the full nth term has got to be the n squared plus the 2n plus 1. Okay? Right, let's do another example so that you can kind of like see this a little bit more clearly, because one example is never enough of this. Let's put a 2 this time in front of the n squared. So 2n squared, let's do plus n plus 3. Okay? And let's find the first 4 terms. So n, un, 1, 2, 3, 4. So the first term will be 2 plus 1, so that's 3, plus 3 is 6. When n is 2, we're going to have 2 lots of 4, so 8, plus 2 is 10, plus 3 is 13. When n is 3, we're going to have 2 lots of 9, so 18, plus 3, so 21, plus 3 is 24. And when n is 4, we're going to have 2 lots of 16, so 32, plus the 4 is 36, plus the 3 is 39. So these are the first 4 terms of the sequence. Now imagine that that's not there, okay? What we would do is we would go, right, how do I get from 6 to 13? Well, I need to add on 7. To get from 13 to 24, well, for that, I need to add on, well, that's 11, isn't it? Add on 11. Don't know why it took me a moment there. And then to get from 24 to 39, I need to add on 13. So we don't have a constant sequence there, but 7 to 11, so that would be adding on 4, and then adding on 4 again to get from 11 to 13. So because I'm getting 4 there, you halve that, and that number goes in front of the n squared. So we're getting 4s here, so that must mean we have a 2n squared. Okay? So we now know there's a 2n squared. So what I'm going to do is I'm going to add 2n squared to my table, like so. I'm going to work out what 2n squared is. 2 lots of 1 squared is what, 2. 2 lots of 2 squared is 8. 2 lots of 3 squared is 18. 2 lots of 4 squared is 32. And then I'm going to subtract the 2n squared away, which will allow me to focus in on the linear term, so the arithmetic sequence that I've got there. So I'm going to do un take away the 2n squared. 6 take away 2 is 4. 13 take away 8 is 5. 24 take away 18 is 6. 39 take away 32 is 7. 4, 5, 6, 7. So I'm adding 1 each time. So that means 1 goes in front of the n. And how do I get from 1 to 4? I need to add 3. So I already had the 2n squared there. So 2n squared plus n plus 3 must be my nth term. Okay, so this is how you can work out the nth term for a quadratic sequence. There's a few more terms, kind of like process involved, but we're going to do a little bit more practice of this in the next couple of videos.